Hello everyone. My name is Amit Shah. I work with Red Hat. I've been working with Red Hat for the last 8 or so years, and I've been working on virtualization, KVM virtualization, for the last 9 or so years, and free software for a really long time. I think 15 or so years. So I have a fair bit of idea of what I'm going to be talking about. However, it's just a 20-25 minute slot, so I can't cover everything. You're free to come up to the Red Hat booth downstairs. I'll be there, and we can talk about it, or you can even catch me after the talk. The computer industry, and especially the age that we are living in, there are these fads that come up every 2 or 3 years, and people get really excited about these things, and they really hype it all up. So virtualization was the thing a few years back, and then it was cloud, and then it's containers now. And there's a lot of misinformation, which I intend to dispel several of the myths in my talk today. It's going to be technical, but not very technical. If you want me to go deep down, feel free to stop me. It's always best to answer questions and give you the information that you want, rather than me going through the slides that I have prepared. So essentially, virtualization and containers, what is the problem they're trying to solve, and why did these things evolve? The traditional way software was deployed was, we had some hardware and a kernel, the operating system running on top of it, with some libraries, runtime, which we now typically call the distribution. We have a distribution running and the application running on top. And this is a monolithic model where just one application runs on one server. And this is how things happened several years back. Data centers like these kinds of deployments because they help contain one application to one server. However, hardware advances made each server have multiple cores, lots and lots of gigabytes of RAM, and the applications stayed the same. The applications were not able to use all these new capabilities that were exposed by the servers. What ended up happening was, we run 32-bit applications on these huge boxes, and all the RAM goes for waste. The cores are also lying idle. And this is not an ideal scenario, because people have pumped in so much money to buy this new hardware, and they can't get the full use out of it. So what it also means is, underused servers take up a lot of power. They need to keep running, and you need lots of such servers to run all your applications, which increases the power costs as well as the cooling costs in the data centers. Also, porting your existing applications on operating systems to a new server means the operating system might have to be changed to take advantage of the server's new features, or even make it to run on the new server. And this is something that people just don't like, because recompiling something or running your existing application on something that is not being tested with is a very slow path. Enterprises don't usually do that. So they believe in, if it isn't broken, don't fix it, let it just run. And this again goes against using new servers for your older applications scenarios. So why not run multiple applications on one server? Well, security is one of the primary concerns over there. If there is an exploit in one of the applications, all the other applications are vulnerable, just because the entire kernel can be exposed. And also, if you want to run multiple applications, the operating system also has to be capable of utilizing all the server resources, which we saw may not be possible in some cases. So this is the data center view. There is also a service provider view, where companies, for example, sell computing resources. For example, web servers, web space, VPS servers, and so on. And in these cases, it's extremely important to have isolation among the various partitions that have been created, or the various VPS servers that have been created. So for example, if one customer is using VPS server 1 and runs a rogue application, it should not lead to a crash in another customer's application space. Resource management is also important for such use cases. If a customer is only paying for 512 MB of RAM and 2 CPU cores, you don't want them to have access to all the cores that your server has. And however, despite all this, they also want to maximize the use of the hardware. They want to cram as many applications on one server as possible. So there are several competing requirements here from all directions. And virtualization containers was one way in which people managed to get all the benefits of all the computing resources they had at hand. So what do admins in general, so from data centers and from the service providers point of view, what do they generally want? Isolation, as in security between each partition. This is absolutely important. Clean environments between each partition, utilizing servers to the full capacity. I'm just repeating, but this is necessary just to enforce the points that are extremely important for all these use cases. Maximize all the computing resources. Applications continue without any changes. In many cases, in many legacy applications, people don't even have the access to the source code. They just have binaries, applications which are running for 30 years, and they want to just not touch it because those applications are doing their job. Even a small tweak is going to lead to a huge loss, even financial. So they just want to run those binary apps as they are and not even touch it. This also means operating systems which those applications are running on also need not to be touched. And so some customers have these kinds of requirements, some not. So all of the solutions that we are going to see to these problems, some are going to address some of these concerns, some are not. So it really comes down to what kind of deployment scenario you have and the risk and cost analysis, risk in terms of security that people want to go ahead with for such deployments. So let's take a look at solutions. Let's build from the extremely unsuitable to more and more, let's say, featureful and secure. So the first is CHroot. I'm sure many of you would have heard of such a thing and even used CHroots. These are useful for clean environments. So if people are doing package builds, let's say Fedora and Red Hat, we use a tool called mock for building packages. So when we write a spec file, what we do is run this tool called mock, which grabs all the build dependencies and builds the package and also deploys it just to test that the spec file written is actually sufficient to pull in all the build recs, so that when this package is supposed to be built on another machine, it does build. There might be some stray packages available on your system, but not on some other build system, which might actually cause the build to succeed on your system, but not on the other. These are the kinds of errors which mock prevents you from making. So CHroot is extremely useful for such cases. Even system recovery, where maybe the kernel is hosed, the newest update that you got. So you boot from a live CD, CHroot to a running environment, which is actually your installed disk space, install the new kernel or the bootloader and fix things. So that is all it is. It's just about file system namespacing. It doesn't really do anything. It doesn't provide any kind of isolation other than that. So this is not really useful in the enterprise. However, this is available, so I just thought of mentioning it. We come to the more interesting use case over here, where we have one kernel running on the hardware and several user space runtimes. This means it could be several distributions. You could have Fedora and Debian running at the same time, and applications running on their own runtimes. This is the traditional containers model. And So containers as a technology is not new. It has been in existence for a really long time. It's just recently that many people are talking about it. But what containers really means is, okay, operating system virtualization is another name for it. As we saw here, we are actually virtualizing the operating system here, and the user space is replicated or different across those virtual machines. What containers does is it has a lot of restrictions added. So each process inside one container is not able to see what other processes are executing on the system. This is really important. For example, if you provide shell services and the user does PS, that user should not be able to do what other processes are running on the other systems, because they might be in use by other customers. And you don't want to expose what other customers are doing on the same server at the same time. Even the PID namespace, which is the processor ID. So all of these are kernel technologies and patches which have gone into the kernel very recently. So process PID namespacing, process namespacing, network and disk namespacing as well. So users of one container should not be able to peek into what other containers are storing. That is the disk namespacing. Network namespacing is packets being sent out by one container should not be visible to packets to other containers on the system, even if there's root available to another user on that container. And these are isolation techniques, obviously. So this increases the security of the container space. We also discussed how resource limiting is extremely useful for service providers, for example, providing quality of service and customers being able to pay for the resources and only getting the resources that they pay for. So C groups is technology in the Linux kernel which allows limiting the access, the resources each container can get. So you can specify that a particular container should only get 20% of CPU runtime. Even if all the other cores are idle, a particular container should not go beyond 20% because the customer is only paying for 20%. So that can be done via C groups. And when we combine all of this, when we combine C groups, file systems, PID, namespace, network disk, all of this, that gives us the idea of a container. You really have a contained environment which is secure, isolated, and resource controlled. Some of the pros and cons: extremely fast load times because there's no kernel to be booted, there is no BIOS to be loaded, and so on. And they can get extremely dense in the sense there's there's very low overhead, which means you can run several containers on one server. And fairly reasonable level of isolation. I have an asterisk there, which means condition supply. You need to be careful about security. There are technologies, SLNX is of course one of them, which helps with managing the security levels of containers. And there's a huge discussion that can be had about this. We can talk about it later after the talk. Some of the drawbacks of the container approach are all the containers share a single kernel. So if there's an exploit in an app which leads to, let's say, a kernel exploit, even if another app which did not have an exploit in the first place, but just because of the fact that the kernel has already been exploited, all the other containers are owned by the attacker. And so that's from the security point of view. But from the deployment point of view, all apps and runtimes have to be able to run on that particular kernel version. If the kernel does not have some config options enabled, which some apps need, bad luck. You just cannot run those apps. So the kernel is going to be standardized, and the apps have to be written with that kind of kernel in mind, which may not always be true in the field. Okay, any questions? Am I going too fast, too slow? Should I? Yeah.
Can you give an example on like when two different containers are independent from the same kernel but to solve like not a good use case for that.
So the question is there a use case when there are two different containers which are dependent on the same kernel?
Yeah, but your last point about at one time and run on the same given kernel.
Right.
Can you give like a real world example when it's not?
Oh, when this is not true? Oh, so as I mentioned, some application might need some special kernel functionality which may not be available on the kernel made available to you. So even if you put your application inside a container and attempt to run it inside that container, it may not run because the kernel does not provide the functionalities that are required by the app.
What sort of kernel functionalities? What are the common kernel functionalities which will cause this issue?
Right, okay, so what are the sorts of functionalities that cause these issues? It can be anything. Let's say there are drivers. Let's say this container is trying to do network routing and a particular kind of driver is not available that is required for talking to a particular set of network hardware. And let's say that is not compiled. The container cannot perform its job. And there can be other things as well, but this is just one example. Right, yeah.
I think another example may be, for example, with Windows supporting containers, IRM containers, and maybe the machine infrastructure architecture, the machine architecture. So you can have a container of Windows can obviously not run on Linux.
For
host.
sure, yeah.
That's one of the drawbacks of containers.
For sure, yeah. They have to, yeah. So the base kernel has to be the same, as in you can't run Windows containers on Linux. Definitely not. Okay, so let's move ahead where we can actually do something like that. We can actually run Windows applications on, let's say, a Linux box. And the way to do that is to, instead of virtualizing at the kernel level, we virtualize at the hardware level. And is this even possible? Does this look right? We have two kernels talking to the hardware, and I don't think that's ever going to work because they're going to have competing resources. So the standard way we solve all problems in computer science is to add another abstraction layer, and that abstraction layer is called the hypervisor. KVM is the hypervisor I'm most familiar with for obvious reasons. So what the hypervisor does is it arbitrates access to the hardware by these various kernels by using functionality enabled in hardware itself. Hardware virtualization is also not new. IBM's Z series, as in the mainframes, always had support for virtualization. They always had to have a hypervisor running. This is technology from the 1970s. But recently, as in maybe about 9 or 10 years ago, Intel and AMD started adding such kind of functionality, such kind of virtualization-friendly instructions to their architecture. That's also because IBM's patents started expiring and they could start doing that in their chips. So this actually allowed hardware virtualization to happen and yield open source friendly solutions. What this means is you can put existing OSs and applications inside a virtual machine and just run it on a hypervisor, and the OS or the app does not realize it has been moved. The entire hardware beneath its feet has moved. It just continues running as normal, and that really is the highest form of containment, highest form of virtualization. Each generation of processors by Intel and AMD make hardware virtualization more and more secure and more performant. One of the killer features people always talk about virtualization is live migration. You can just move a running virtual machine from one host to another host in a data center or even across data centers, and applications don't even notice. They notice slight degraded performance during the time of migration, but they don't realize that they're being moved across geographies or whatever. So the pros with hardware virtualization is that this is the most secure form of it. Even a root exploit or a kernel exploit inside an application is contained within that virtual machine. Other virtual machines on the host are not affected. Only if the exploit can go out to the hypervisor level is this possible? But the hypervisors are so tiny, so thin, and well protected that there are not too many cases that we've seen. Overheads keep getting low. Of course, containers can get, as in deploying containers is extremely dense, very low overheads. Overheads with virtualization is more. Even booting a virtual machine, you need to, for the x86 world, you need to boot the BIOS, then load the kernel, boot the kernel and so on, the bootloader and so on. All that is not needed for containers. That's needed for virtualization. There are some cons. It needs emulation of devices, which can get slower. Also, there's lower densities. We already covered that. Emulation of devices, we can always have faster device emulation. We always work towards this. And we can, of course, get very close to bare metal speeds with virtualization even today. Hardware virtualization actually enabled cloud providers to come up. So services like Amazon EC2, Google Compute Engine, and so on. So they use these commercial off-the-shelf systems and form these data centers, and they expose all these virtualization interfaces. And when we combine those solutions, when we have the hypervisor running as well as operating system level containers, OS virtualization containers, this is the kind of view we get. And this is really important because what we get from, let's say, Amazon EC2 is a VM. And if you want to maximize the usage of your compute resources that you're getting, you can run containers within that VM. So this was the ops side of thing. The dev side of thing is also, the common developer refrain is, well, it works on my setup, why can't you make it work in your setup as well? And so that's what Docker really does. Docker is a package management solution. You'll note till now I haven't mentioned Docker, I've mentioned containers, but Docker usurped the term containers to mean what they wanted to, but containers have been in existence for a long time. What Docker really did was come up with a packaging format and a deploying format. So they integrate all the runtime dependencies that an application might have, and you can easily load it inside a container, inside a Linux container, and have this setup ready. It's not always a good idea to do this because developers, they say, okay, this works, let's deploy it. But there are limitations to how much you can deploy directly from a developer environment to production, because you need to vet the applications and the libraries for security issues before you actually deploy in production. Okay, we're kind of running out of time, but I have a bonus slide about unikernels. This is also something that people have been talking about recently. Unikernels are really stripped down versions of applications and runtimes and kernels. So one of the facts is you can just get compute resources directly from, let's say, EC2. So you're running on a hypervisor. What you can do is, instead of booting a full-blown operating system under that hypervisor, the hypervisor is going to provide you some services. Write your applications in such a way that they directly work on the hypervisor, like a traditional app would on an operating system. And you cut out a lot of user space, kernel space switching within the VM. And that's what unikernels do. So they are faster. Intel is working on some technologies to build faster containers, and they're adding some instructions, they're adding some smarts to the chips, so that things like very fast virtual machines, which are almost like unikernels, are possible. And that's it. So you can see me later at the Red Hat booth or ask me questions outside. Thank you.